Testing. Alrighty. Alrighty, everybody, let's get started. We have a kind of packed day because we have a quiz and stuff, so I want to give you guys as much time, so we're going to get started right away. For anyone coming in, midterms are over there. Please don't grab anyone else's. I'm kind of watching. The grades are inside the cover, so right for FERPA stuff, you don't see each other's grades. I'll be free if you have any questions on them, probably after class. Okay? Ready, so let's get started. This is Fluid Mechanics, Lecture 14, and we are starting Chapter 7. So I think we're on like week 7 now. We're more than halfway done. So if you're still here, awesome. We're going to keep pushing through, and we're having a good quarter. So, okay, and for these videos, just to cite sources, a lot of my work came from this textbook. Some of the lectures, slides I referred to from Dr. Abadi's. Okay, so agenda. Since last lecture, I didn't get to talk too much in person right at a recording for you. We're going to highlight some important things from Navier-Stokes equation really quickly. I'm not going to go through details again because we already went through that in the video. And then we're going to start Chapter 7, which is dimensional analysis, similitude, and modeling. And we'll kind of talk about that. And then I have this thing I was working on last night. I called it Engineers Go Acting. Why? I try to make these lectures more fun for everybody. So you'll see. It's not a lot of work. It's no work at all. It's just me talking and just trying to make it more fun. Okay? You'll see. And then we're going to talk about the Pi-Buckingham theorem. That's kind of the main point of our lecture today. We're going to do an example. We're going to talk Reynolds number, which is very important in fluids. That's maybe one of the topics in addition to Navier-Stokes and Bernoulli you should probably remember. We have announcements and then quiz 5. We're going to do it once this is all done. So quiz 5, right? You should have your equation sheet. You're allowed a full page. This time I am looking pretty strictly at your equation sheets that are no examples, no fully written out solutions, because it's pretty, if you studied the homework and you understand it and you kind of remember it, you should be good for the quiz. So that's why I'm going to look through your equation sheets. No written out examples or solutions, okay? Okay, any questions what we're going to do today? Okay. Let's get started. Okay, really quickly, right, Navier-Stokes, I hope everyone watched the recording. I had an example video that, sorry if it was kind of bad quality, but I didn't have like an iPad like I said, right? I had like a GoPro mount on my chest and I did a problem. So I think I got the point across. If I had a fancy iPad, it definitely would look a lot better, right? So I guess just a heads up, I really do like the problem I did on that video, so I picked it. So when you study for the final, that's something I recommend you review, okay? So this slide is very important. If I have concept questions on your final, it's probably gonna come from this for Navier-Stokes, okay? So I went through every single individual term of Navier-Stokes and what it means. So this is conceptually very important so you know what Navier-Stokes is. And the main idea, right, is there's two equations to this. There's the conservation of mass, which is your del operator, which is just partial derivatives, right, with x, y, and z, dotted with your velocity vector, x, y, and z is equal to 0. And that is just right here, right? So if this is 0, this is conservation of mass, and that doesn't change, right? And then everything else is explained. I'm not going to go through it again. I'm just saying this slide's very important conceptually. Okay, right, this is my mean that I keep pulling up. So this is the polar coordinates of Navier-Stokes, still very important. So I hope you did that review problem in your homework. This used to just be Bernoulli's, but I changed the meme a little bit. So now that it's this, I think this slide is really helpful because I don't think they have this in the textbook. So I hope moving forward, if you ever need the Navier-Stokes equation or you need a reminder of what each term means, you refer back to this slide. That way you just understand conceptually. And then I hope for people that watch the lecture, right, there was this thing called the Millennium Problems. And I believe there are 7 mathematical problems that need to be solved. So if you solve any of those, you can get up to $1 million. It's a good way to probably not retire, but it's a fun thing to do. Any questions on this? I thought it was kind of interesting. Make your lecture a bit more fun.
I think one of the professors here is trying to.
Oh.
Dr. Loretto.
I had Dr. Loretto for Calc 3. That's awesome. Maybe I'll talk to Dr. Loretto. Maybe just for fun. I don't know if you have all played this this game called it was like Imposter. It's like a training game. We're not going to play the game. Maybe on a count of 3, we're going to point to someone in class that you think that has a chance of solving it, just for fun, okay? And then if you don't want to point at anyone, you can point at yourself, okay? 1, 2, 3. Point at somebody. Who has the most? Is it Tony over there? Okay. I will write. Your last name is Schwartz, right, Tony? Yeah. Okay. I'll remember Tony when Tony wins $1 million. We. Okay. Alrighty. All right. Introduction. We're going to start chapter 7 now. So, why dimensional analysis? It was pretty surprising to me when I was going over what we're going to learn. We do these multivariable calc stuff, partial differential equations. You know, my great, really smart students, we just came from a really hard chapter, and then we go to dimensional analysis, like what is going on? And it's actually pretty interesting, right? It's important still, not as important as Navier-Stokes, but the main purpose of it is we're not just learning to cancel units just to cancel them for answers. There is this topic called a dimensionless parameter, and I'll explain that in a bit. And that's really important because that helps you graph fluid mechanics equations in a relationship. So I'll go over what a dimensionless parameter is, but that's the main reason why we are going through this dimensional analysis. Similitude is basically being able to acquire experimental data in a lab. So you're basically a simulation, right? So right, even at my work at Boeing, we have simulation centers. I even was fortunate enough to fly a flight simulator. That was really for pilots. That was kind of fun. So they use experimental data in real-world applications. Right, these are just topics. Models, I guess I didn't save my last thing last night, but it's basically just if you need to model something down to scale for a solution, and then you get a prototype, which I will show you in a bit. A prototype is the actual scale that you're going to do your testing on, right? So main idea, what we're going to talk about is this dimensional analysis, and then the introduction will get further about this, okay? So that's what we're going to talk about. Okay, so before we start this, reminder, right, we have kind of 2 unit systems. We have the MLT and the FLT. Right, MLT is mass, length, and time for units, right? So mass is like kilograms, length is like meters, time is in seconds. And there's also the FLT system, which is force, length, and time. And when we do dimensional analysis, we're kind of going to work off of one of these. Make sure you don't do both, right? You have to pick one or the other. And this equal sign with a dot above it just indicates that they are dimensionally equal. So the units are the same. And if you need to relate from the FLT to the MLT system, this is the equation that you'll need, or the definition, I guess. Right? So a force is equal to the mass times the length divided by time squared, right? That's just Newton's second law, F equals ma. And this is in your textbook, table 1.1, we went over this, I think, the very first lecture. So for every single dimension, right, you have your FLT and MLT system already written out. So if a question like this pops up in your exam, if you know the units, you can kind of just write them, right? But if you really want to put this on your equation sheet, you can. But it's kind of long, right? But you can kind of put your FLT or MLT in whatever units that you get. Okay, so this is kind of my fun idea to get this topic introduced and why it's important, okay? So I guess let's go through the pictures first, right? I don't watch a lot of engineering movies. So I Googled them. I couldn't really find much. I don't know if your cohort does this. My cohort had like a movie night or something, and we watched Interstellar. I was not a big socializer in school because it's really busy. So I just went to study. I didn't really go. But right, if you didn't know, right, Tony Stark's a mechanical engineer and Iron Man is fictional. I actually wrote my master's statement of purpose. I was like, my hook was about him. And then Hidden Figures, I was not forced to watch it, but it was an extra credit assignment in high school for me. So I went to go watch it with my friends. Does anyone know who this is?
I don't remember his name, but he's from Rogue One. He's the engineer who built the Death Star.
Right. This is Galen Erso. Thank you. That is exactly who that is. Okay, that was just for fun. So I need 2 volunteers. You don't really have to do anything. You just have to sit there and pretend I use your name for my story that I'm going to tell you of why this topic's important. It's just for fun. Thank you. Carlos is 1. Okay, McKinnon, right?
Yeah.
Okay. You don't have to get up or anything. It's just you're part of my story. I just want to use 2 names to make it more intriguing to you. All right. And like I said, we are not actors, right? Because that's why we're studying engineering. So, okay. All right. So, Carlos and McKinnon, they got hired at this new company graduating out of college. Right? I don't know if they want to do fluid mechanics, but let's just say they do. So they got hired to Utah Pipe Fluid Engineering Corporation. I made that up. It's not real. I was trying to get a really good logo. I don't know if anyone took the SolidWorks class yet. I don't know if Captain Anderson teaches that still. Your guys' project was really fun and good. I don't know if it was still like the bracket for a boat or something like that. Like I actually thought it was for a real company. Like Captain Anderson is a good actor. So when we got to the end, I was like, is this actually going to be for a company or something? And then, wait, is that class already over for you guys?
Yeah.
And then
There's some people still taking it.
But they're taking it with like different professor. Yeah.
okay, so it's different.
But,
So
you know, we took it, and I mean, like for the first few weeks, we were like, damn, we're like actually doing something.
right, yeah.
NDA, and it was like, whoa.
So I also believed like it was for something. I didn't know it was just it was obviously just an assignment, but I thought it was real. So that was kind of interesting. So I was like, maybe I'll try to make something more official. But then it was 3 a.m. and I was like, I'm just gonna copy and paste the fluid picture and put that on there. And like I always say, like I really care about you all doing good and getting a good valuable fluids course. So I have been risking my health and mental health so you guys get good content. So I hope you enjoy this stuff. Okay. And like I worked, not to digress, right? But I've worked full time and did my master's program. And it's pretty tough for anyone that does that. And I'm sure someone in here is going to go to work and get their master's paid for. Although it's maybe not as stressful, this is definitely a lot more work because you got to learn and understand everything and make your lecture content. Okay, anyways, for people coming in, I have a fun story. I want to catch you up because I don't want you to start late in the movie. So we have 2 students, right? We have Carlos and McKinnon, and we're pretending they just got hired at this really fancy Utah pipe fluid company. Okay? Why am I doing this? Is to introduce our topic for Chapter 7 in a fun way. Okay, candidate comparison. Just for fun, right? Student A, we'll say it's Carlos. I will not put your name in there, so when I post the slides, it's not in there. Well, just for fun, why did you pick Emmy?
I guess because you can actually apply stuff in real life, I guess.
Apply.
I kind of just got into it because of like cars and stuff.
Dude, me too. Cars. All right.
It's in my name, so I guess.
Here's another fun thing about me. I wanted to study. All right, we gotta hurry up. I wanted to study marine biology, but because I was into like Pokemon and stuff, and I wanted to like explore, whales and things like that. And my mom said if I studied marine biology, she wouldn't pay for my college. So I didn't have money to pay for college, so I picked ME, and I like cars. That's kind of why I got into it too. But it's awesome now, and here I am teaching your fluids class. Okay, McKinnon, why do you study ME?
Robot dinosaurs.
Robot dinos. Okay. Like in Power Rangers, or what are we talking about?
For research or like the animatronics they used to film Jurassic Park.
Oh, okay, nice. All right, I'll put you on the spot, Carlos, because this might be asked in your future interview. Why did you want to work for this piping company?
The piping company directly relates to
Okay.
Fluids going through it as exhaust.
Okay, it's the right answer. All right. McKinnon?
Actually understanding the flow of fluids is interesting.
The flow of fluids, okay.
Oh, hydraulics.
Hydraulics. Okay.
Exhaust in there.
All right, Carlos, favorite fluids topic so far?
Probably Bernoulli's.
Ber-
Something like that. Bernoulli's equation.
Oh my goodness, I butchered that.
There you
All right, favorite fluid topic so far? McKinnon?
Navier Stokes.
Yeah, all right. So look at this. Look at these two students. These are the two most important equations in our class. Keep that in mind for the final, right? That's probably going to be on there. Those two are very important. Okay. These attributes, that's not them, but I just put it in here to go with my little story here, okay? Student A, Carlos, very hardworking and puts a lot of effort in acquiring results regardless of tedious work. Even if it's repetitive, Carlos will get it done, okay? McKinnon, works smarter, not harder. This may be quote unquote a bit lazier, but there's actually a quote that says, right, the lazy engineers are actually maybe people you want to hire because they do things more proficiently. I think I'm a little bit lazy, but if I need to go to this route, I'll do it too. But right, so McKinnon tries to find the most efficient solutions to problems, okay? Okay, so your manager, your boss assigns you a task, right? These are just assumptions because we're in a class, okay? Steady flow, right? Less like laminar flow, incompressible fluid, density is constant, Newtonian fluid, a linear relationship for your shear stress to your viscous forces, smooth-walled, right? No bumps in your pipe, horizontal pipe and a circular pipe, just assumptions. Task, okay? So what your manager asks you to do is, how does pressure drop per unit length develop along a pipe based off of variables that will affect the pressure drop? So grammatically, this kind of sounds weird, but I had to keep this bolded part in because this is what we call a pressure drop per unit length. So conceptually, pressure drop is if you have a long pipe, right, and you take your pressure at one point to the second, there's going to be a pressure difference, usually because there's friction involved, right? So that's delta P, we're going to call it. So when you see delta P, it's just a pressure difference in the pipe. And then that's technically unit-wise is divided by length because it's pressure drop per unit length, okay? And from English to math, right, this per usually means division, okay? So this could be both of you or anybody, right? If you were to think of this pressure drop in a pipe, do you have any variables in mind that would change this pressure drop that we've learned about?
Changing
Height of?
like the inlet and outlet of the pipe.
Right. That would contribute in, but we're assuming horizontal pipe, so it's not changing height for this problem.
You're changing velocity. Or
Velocity is good, yep. Anything else?
Viscosity.
Viscosity, yep. Diameter of the
Pipe.
Yeah, pipe. Okay, perfect. So here are some of the variables that could contribute to the change of pressure. So you'll see when I do example problems, I write this kind of as delta P subscript L. I typed it in like the PowerPoint equation writer, and the L made it look really weird, so I left it out in the text here. So if you see delta P subscript L, that's just change in pressure per unit length, okay? This is, right, your function is comprised of these variables. So we already said some of them. D is diameter, rho is density, mu is viscosity, and V is velocity. Okay, so there's some kind of function, and if you vary these variables, your change in pressure, or your pressure drop will change, right? And this kind of is similar to your project, right? You're gonna have an equation, you're gonna vary and show the results. So in a way, they're kind of doing their project as well here, right? These are, I don't know why my N got cut off there, but these are dimensions here for these respective units. All right, velocity, mass over, meters over seconds, right? Diameter's length. Okay, so Carlos he works hard and he grinds in his lab, he goes to his experimental lab, And he basically went through some kind of, tube setup, and he would make graphs for everything that he varied, right? That Carlos varied. So Carlos would keep all except one variable constant. So for example, this graph A, Carlos kept diameter, density, and viscosity constant the same in the experimental setup. Okay? And then Carlos varied the velocity. So maybe he'll increase the velocity from 10 to 12 meters per second, 15 meters per second. And then for every velocity, he would measure a pressure drop, right? You could maybe have a manometer, piezo, I forgot what they call it, piezo something tube, right? Something to measure pressure. So, and then, right, Carlos needs to make another graph because Carlos needs to see for the diameter, right, how does that vary in the pressure drop? So then Carlos keeps the other variables constant and then varies diameter. At different diameters, how does the pressure drop change? Okay, and then this is just one curve too, right? If there are different initial conditions, you can have multiple curves for each graph. Okay, and then so on, right? So then keeps the other variables constant, Carlos will vary density. Keeps the other variables constant, will vary viscosity. So there's multiple graphs, right? And the small chance that Carlos doesn't get the velocity his boss wants, right, is going to be missing in the graph. Okay, any questions on Carlos's work here? Okay. All right, so McKinnon, right, like I said, this works maybe a little bit smarter, not harder, in this example of our fictional story. So McKinnon discovered dimensionless parameters. And I am going to go into detail of how we get these, but I'm just going to show them to you now so you can understand conceptually why they're important, okay? So instead of having all these multiple graphs, right, because Carlos is going to turn in like a 60-page stack of paper to his boss of all these graphs, right, McKinnon is just going to have one graph here, okay? And here, I'll show you how to get these. These are dimensionless parameters. So if you put your MLT system or your FLT system into either this ratio here or that ratio there, you'll get a unitless parameter, okay? And now, in the singular graph, right, if you vary diameter, it's going to lie along this curve, right? If you want to vary velocity, it's going to still lie along this curve. If you want to vary density or viscosity, right, it's still going to lie along this curve. Right, compared to this, right, you need to have multiple curves depending on what you're testing. Okay, any questions about the work that Carlos and McKinnon did? Okay, right here is just showing that the units cancel out. And then this will be our final answer for the example I'm going to show. But you basically write your y-axis as a function of your x-axis. And that's just your normal, right, like a y equals mx plus b. You have a function y, and it has a variable x in it. So that's essentially what this is. This phi, right, we have so many Greek letters. This is just your function. They don't want to call it the f like we did earlier. Phi is your dimensionless parameter function. Okay, we're getting close to our story here. End of story. So student A, Carlos, brought 50 stacks of paper to the manager, and the manager is like, oh, nice work, this is awesome. And then maybe the manager's like, oh, did you do 40 meters per second? And Carlos is like, maybe no, maybe I only got like 37, is that fine? He's like, yeah, maybe, that's good. Compared to McKinnon's work, right? McKinnon had one sheet of paper with one graph only, and you can pretty much put in any variable in there, right? Depending what the boss wants. Okay, so that goes to my next point, right? Accounts for the variables already. And then just for the funny ending of our story, it's like a joke in the workforce, right? We always have performance review. Technically, student A got a met expectations. And that just means kind of, I don't know, the majority of people will get this, basically. When you start working, you'll have performance reviews. And then student B got a promotion to level 2 because of their efficient solution. Okay, that is the end of my story. I didn't do it to waste your time, right? I wanted to make it fun. The whole point is for these dimensionless parameters, student B had to only have one graph and one piece of paper that covers all of the relationships in the equations. Okay, any questions on our make-believe story here? Okay, and this was kind of inspired from, I read the textbook, they don't have this obviously, and I was just looking at random YouTube videos, and this professor from, I think, Colorado had something similar. He didn't have like a story, but I went into more detail, that'd be more fun. Okay, so how do we get these dimensionless parameters? Okay, so these are the dimensionless parameters that we're gonna look into. And this is important because this is basically what your homework is gonna be about. I already posted it on Canvas. Okay, so this just shows, right, these units cancel out to a unitless parameter. And the way we find these, right, because I just gave them to you, is called the Buckingham pi theorem. And interestingly enough, right, this is pretty applicable to real world when you're in the workforce, right? So I've seen equations at like Boeing that they had to use this approach to find an equation that we use at work. So that over there is Buckingham, and does anyone know who this is? Bucky, right, from Marvel. So that'd be kind of funny. I was like, I could have done that for every single equation writer that we've met, but I didn't want to do it for every single one because I don't know, it might be kind of rude that I'm just putting an actor next to their face. Maybe they only want the equation. Okay, we're doing, let's see what time it is. Okay, doing good. Okay, so the theory behind Buckingham pi theorem. So this is a little bit long, right? For my slides, I really just like to have bullet points to keep it nice and short for you. But I wanted to copy and paste this because this is a pretty good idea of what it is. So let's just read it together. If an equation involving k variables is dimensionally homogeneous, which is like the same, right? It can be reduced to a relationship among k minus r independent dimensionless products. I will go over what this k minus r is in a second. Okay? Where r is the minimum number of reference dimensions required to describe the variables. So most of the time, this r will be 3 because you'll have your either MLT, right? There's 3 different dimensions, or your FLT. Right? And this will all make sense once I go through the example, right? I'm just kind of giving you the theory right now. So dimensionless products or dimensionless parameters, right? Like for example, these two, I referred to these as, or what it's referred to, they're called pi terms in the Buckingham pi theory. So when we're saying we're solving for these two values, we're saying we're solving for these pi terms. And essentially, this is just showing how you're going to put your answer at the end. Okay, so if you have u1 as a function of u2 and so on, we're going to do the same with the Buckingham pi theorem, where we call pi1 as one dimensionless parameter, and it could be written as a function of other dimensionless parameters. So pi2, pi3, pi4, and so on. Okay, so I was going back and forward of what would be best. Should we go through the steps first? Should I do an example first? So I think this won't make a lot of sense right now when we go through this. So I'm just going to have an overview so you understand the steps, and then we'll do an example that will hopefully really sink this in for you. Okay, so there are 8 steps. Technically 9 in the textbook, but looks like we combined steps 8 and 9 together here. Okay, so step 1, list all the variables that are involved in the problem. Let me get something really quick. So that just means you're finding all these variables that we did in step 1 in our story, right? For your pressure drop, what variables or dimensions are going to be involved in how this changes, okay? So that is step 1. List all the variables that are involved in the problem. Step 2, for each of those variables in terms of basic dimension. So you're expressing each variable that you listed up there as either your MLT system or FLT system, right? So for example, density is your mass divided by your length to the third power, right? And I just put this here because if you need to go back and forward from FLT to MLT, you have this definition right here. So basically, right, that is step 2 is right here. And I'm going to go through this again. Okay, step 3, determine the required number of pi terms. Okay, so the k minus r in the previous slide, this is what it means. So k is the number of variables in the problem from step 1. So as that k is whatever number you have listed in step 1, right? If it's density, viscosity, diameter, velocity, that's 4. Okay, your k would be equal to 4. Your r is the reference dimensions used, such as FLT or MLT, once you do step 2, right? So you'll see it when I do it, right? But you'll see in step 2, oh, out of all of my variables, I see an F. Okay, that's 1. I see an L. Okay, that's 2. I don't see a T. Okay, there's only 2. So R is equal to 2. Most of the time, you'll see R is equal to 3, right? Because we're going to use all FLT or MLT. Okay, so step 4, this is the trickiest step, in my opinion. You select a number of repeating variables. So these repeating variables, I go into more detail, but this is how you're going to solve for these dimensionless parameters here. Okay, so where the number required is equal to the number of reference dimensions r. Okay, so I made a second slide here, more in details of selecting your step 4. And like I said, this will make a lot more sense once I do the example. Okay, I'm just giving you an overview of what these steps mean. So select a number of repeating variables where the number is required to equal the number of referencing dimensions, r. So you're going to pick, out of these variables, you're going to pick a repeating variable that you're going to be using to solve for the dimensionless parameter. And here are some additional rules that I wrote down. The textbook has some of this, some of it doesn't, but these are just rule of thumbs when you're picking, because if there was to be an error in this whole problem, it's probably going to be in step 4. So don't select a dependent variable, meaning if one repeating variable, if you have a repeating variable multiplied by another repeating variable, it cannot basically combine to another variable. It can't be dimensionless. And you'll see what I mean once I do the example. Okay, and then like I said here, all of the repeating variables you pick, once you do the units, they all cannot be dimensionless, or else it's not going to work. Okay, and all the variables eventually should contain your FLT or MLT system. Do not select a variable that is dimensionless. That means like theta, right, an angle, or in radians, right? It's dimensionless. Okay, and then step 5, you're basically going to solve for your pi terms there. That's, in short, what it means. And I'll show you how to do that. It's just algebra. Okay? Step 6, you repeat step 5 for every repeating variable. Step 7, you check all the resulting pi terms to make sure that they are dimensionless. Right? So, like I said, these are dimensionless. So a quick check if you're doing a quiz or an exam, if these are not dimensionless, there's something wrong. Okay? And then 8 is we just arrange our answer into that format I showed you, where pi1 is a function of the rest of your pi terms. Okay. So like I said, this probably doesn't make a lot of sense right now, but we're going to do an example, and then hopefully it will make more sense. Let's see if I can turn on the front lights here. That's as bright as it gets, I guess. Alrighty. This marker's not good. Okay, we'll do an example. Skewed. All right, sorry, this fox has got to go. It's been on here for too long. Okay, and then let's position our camera so it's kind of able to see the board. Let's see how that looks. Okay, we're doing good on time. We'll just kind of leave up our problem. So we're going to do the Buckingham pi theorem for our pressure drop here. And if we do it right, we should get the dimensionless parameters in our fictional story that McKinnon got. Okay, I think that's as good as it's gonna get. Okay, so if you want, you can write this down. I'm gonna kind of write it all on the board, but I think it's more helpful if I have the steps up for us. Okay, so this is the one time I'm not gonna do given, finds, and assumes because we're following steps here, so we'll get a little leeway there, okay? So step one, list all the variables that are involved in the problem. Okay. Right, so that's already given to us, right? So your delta P subscript L as a function of diameter, density, viscosity, and velocity. Okay? And if for anyone, does anyone here read the textbook? Okay, awesome. So I go back and forward, right? If I remember when I was a student, if the lectures were enough, I would just do the lectures, but if I really need to understand more, I'd go to the textbook. There are these steps in the textbook, but they have like paragraphs written under each step, and it's very helpful to understand how these work. So I would recommend reading that if you have time. But this is condensed of the steps right here, like a short sentence for each. Okay, step two, express each variable in terms of the basic dimension. So, okay, so our pressure length, right, that is equal to force divided by area squared, but it's per length, right? So if it's per length, it's going to be length cubed. Okay? Diameter, that's equal to just length. Viscosity, I'll just give this to you. It's force times the time divided by length squared. If you look at viscosity units, if there's a kilogram, you have to use this to make sure it goes back to FLT system. Okay, and then right, velocity, right? That's just meters per second. So it's length over time. Okay, so easy steps so far, right? Just make sure everything's right. We are missing. Sorry, I don't. Yeah, we're missing density. So we'll put density over here. So density is force times time squared divided by length to the fourth power. And right, density is usually a mass over volume. So like I said, if you use that conversion, that F equals mLT to the -2, you will get this density. Okay? Just make sure everything's right. Ft squared L4, FTL squared LTD. Okay, good. So, okay, step 3. Step 3, determine the number of pi terms, k minus r. So k equals the number of variables in problem 1. So, right, k here we have 1, 2, 3, 4, 5. Okay, pretty straightforward. That's k. Okay, and then we ask ourselves, oh, what is r, right? So r is number of reference dimensions in step 2. So this basically means if you see an F, if you see an L, or do you see a T? Okay, so we're going to go through step 2. Do I see an F? Yes. Do I see an L? Yes. Do I see a T? Yes. So that's all 3, right? So that means R is equal to 3. Okay? And then, so number of pi terms is equal to k minus r. 5 minus 3 equal to 2. So that means we're going to have a pi 1 and a pi 2. Make sense so far? Okay. Step 4. Okay, so step 4, select a number of repeating variables where the number required is equal to the number of reference dimensions r. So r is 3, so we need 3 repeating variables. And when you pick these repeating variables, you're picking from these 5 that you have in step 1. So if I were to maybe make a note here, I would say repeating variables you pick from step 1. Okay, so they're also in step 2, right? So there's 1, 2, 3, 4, 5. So we need to pick 3 repeating variables. And I guess to save us some time, for this problem, we're selecting d, diameter, velocity, and density. I don't like how this d looks. Let's fix that. So I'll probably get a question later, right? What if you select the wrong repeating variables? You will just get a different answer, and if it's dimensionless, it's technically still correct. The only reason why I am picking these is because we get the values in our example problem that McKinnon got, because one of those values is Reynolds number, and the other one is the pressure drop equation. And the engineers just made a name for that equation, so that's why we're picking these 3 variables. Okay, so these 3 came from our 5 up there. And so note, all of these are independent. Okay, so if you were to plug, you basically can't get, if I multiply these 2, I can't get another one of my repeating variables, because it will essentially mean that it's dimensionless. And your repeating variable, your step 4 here, it cannot be dimensionless. That's a big no-no. Okay, so if you plug all the units into diameter, velocity, and density into here and multiply them out, you should not get 0 there. Okay, so now let's go into step 5. I'm going to do step 5 over there because this is kind of the most work in the problem. All right, does anybody have the time on them? 9:30. Okay, I'm doing okay. Thank you. Well, 30 minutes. Okay, step 5. So now it says form a pi term by multiplying one of the non-repeating variables by the product of the repeating variables. So let's make this clear then, right? This is our repeating. Okay, and then the other ones are not the repeating. So that is 1, and then mu. Not. Okay. So variables. Wait, we're on step 5. So form a pi term by multiplying one of the non-repeating variables, meaning one of these variables, to the non-repeating variables, all of them. Okay? So I hate how there's a line here, but that's okay. So pi 1 is equal to, let's start off with the pressure drop. So delta P with respect to L, diameter. I'm going to explain why I'm doing this in a second. Okay, so, right, you take your non-repeating and you multiply it by your repeating variables, dv rho, and you raise them to a power of, you can name these anything. I'm just going to name them ABC. And the reasoning for this is we're going to solve for these exponents so that when you plug in these units here, they're going to be dimensionless. Okay, so that's kind of the goal of the game. Basically get a dimensionless parameter. Okay? So now I'm just going to plug in everything from step 2 into these terms right here. Okay? So, okay, this is force over length cubed. Okay. Times length to the a power, length over time to the b power. Let's not. It's not density. Okay, and then we have our density, right? What's density over there? We have force times time squared over length to the 4th power raised to c. Okay. We good so far? All I did was, for each of these variables, I plugged in what I defined in step 2. And step 2 you get from table 1.1, or you can figure it out yourself. Okay, so now we basically want this to be f to the 0 power, L to the 0 power, and T to the 0 power. Why do we want those all to the 0 power? Because that's how we get a dimensionless variable. Okay? So what I'm going to do now, I'm going to go through each variable and solve for the exponent. And you'll see what I'm doing here in a second. So let me write it out and let me explain. Okay, so I look at this term on the left, I look at all my f's and see what power they're raised to. Okay, so there's an f here, that's technically f to the 1 power, right? There's another f here, right? And this is raised actually to the 2c, should be 2. Oh, no, sorry. There's an f right here, that's raised to the c power, right? Because this exponent gets distributed. And that all equals f to the 0 power, right? So, and if you remember power rule from your pre-calc class, I used to be a TA for that class, If you multiply common bases, you add their exponents, right? So that's just an algebra rule there. So now, right, this becomes 1 plus c is equal to 0. Okay? So now you get c is equal to negative 1. Make sense? Hopefully? Okay, next we do L next, right? Okay, so we do the same exercise. We go here. Where do we see L's, right? So you see an L in the denominator here. So that's on the denominator. So that's L to the negative 3. L is right here. It's L to the A. Another B there, L to the B. And then this is L to the negative 4 times C. Okay. That's good. So this means negative 3 plus A plus B minus 4C equal to 0. So we do not have everything we need yet, right? Because we have C, but we do not have A or B. So let's go move on to the next dimension for time. Okay, so we look on the left-hand side of the equation. There is a t in the denominator, right? So that's technically t to the negative 1 if you bring it up to the numerator. So that's t to the negative b. And then there is one more t right here, okay? That is t times 2c is equal to t times 0. Okay, and then following our same steps, negative b plus 2c equal to 0. Okay, so we have c, right? So let's plug that in here. So b is equal to 2c is equals to negative 2. Negative 2. Okay. Now that we have C and B, we can now solve for A, right? So okay, so that's going to be negative 5, negative 4 plus 4. Wait, no. Negative 5. Make sure I plug that in right. Negative 3. A. B is negative 2. C is negative 1. One second. Might have made an algebra mistake somewhere. No, A is 1. Oh, wait, no, sorry. C is negative 1, B is negative 2. Sorry, yeah.
That equation, it's negative 3 plus A plus B minus 4C. So when we multiply the negative 4 by your C value, which is...
Yeah, let's... Okay, let's just fully plug it in, huh? So we don't mess up. So we'll do B is equal to 4C minus A plus 3, right? 4C minus A plus 3. That is 4 times negative 1. Oh, wait a second, sorry. We're solving for A here, my bad. Okay, so A is equal to negative B plus 4C plus 3. B is negative 2, so that's going to be positive 2. 4 minus 1 plus 3. That's right?
Shouldn't that be a negative 4?
Yeah, because it's 4 times negative 1.
Oh, sorry, -4. I went to bed too late last night. Okay. So it's -2 and +3 is -1. Sorry. Okay. A equal to -1. Okay. Okay. That makes sense how we solve for A, B, and C. Sorry, that took a little bit longer than I thought it would.
Sorry, is
Yeah.
A positive 1? 2 plus 3 minus 4.
Right. 2 plus 3 minus. Sorry. Yeah. +1. Okay. But you get the idea, right? Solve for it algebraically. Okay, so now we get to solve it, put these back into pi 1, right? So pi 1 is equal to delta p L d. I don't like that d. D to the 1. So sure, we'll put it here, d to the 1. V to the -2, rho to the -1. Okay, so this is your pi 1. Any questions? Okay, we're gonna go really quickly through the next pi term, but we're running out of space. I guess I'm gonna have to do it over here. Okay. Sorry, people on that side. Okay, so step 6 is repeated for the other pi terms, right? Okay, we're going to do this a little one faster. So we have pi 2 is equal to non-repeating, which is mu times diameter to the a power, velocity to the b power, density to the c power. Okay, we plug in all of our step 2 units into here, right? So we're gonna get, let's see, step 6. Okay, so ft L squared, L to the a. This is gonna be length times time to the b, and then our density here is ft squared L to the 4 times c. Okay, so we just plug in our step 2 units into the L there, or to our variables there. Make sure that's right. Ft L squared L to the a db. Okay, right, so this equals to f to the 0, L to the 0, time to the 0. Okay, so now same exercise, right? We do f. Okay, we look at the left-hand side. Where are our f's? F to the 1. Okay, we okay over there? Sorry, I'm a little boring here. If I had another movie story, I would. I had this person in my class that he would drink 2 full-size cans of Red Bull and still get knocked out sleeping. That was our mechanics of materials class. I remember. I don't know who teaches that now, but Dr. Bruce was awesome. I love that class. That was my favorite. That's why I'm a stress guy. Anyways, okay. I'm digressing, as Dr. Bridge would say. Okay, so, okay, f to the 1. This is f. That is a not nice looking C. It looks like an L. Let's rewrite that. Okay, f1, f to the C equals f0. Okay, that. Good. Okay, good. That is 1 plus c equals 0. C equals -1. For people writing, I'll give you a second to write that and catch up. Okay, we look at the left-hand side, right? Okay, L is -2. There's an L over there. That's L to the B. There's an L to the A too. Let's write that first. L to the A, L to the B power, L to the -4 times C. Okay, let's make sure that's right. Okay, so we have -2 plus A plus B minus 4C is equal to 0. We don't have everything yet, right? So we're gonna go to the T. Okay, so we have T to the 1. We have T down here, T to the -B. And then we have T to the 2C. Okay, let you guys look at that and catch up. Okay. Must be full here. This is technically L to the 0. Okay, so we have 1 minus B plus 2C is equal to 0. Okay, we plug in C is equal to -1. 1 minus B. This becomes -2. So B is equal to 1. -1. Okay. All right. You guys can check that. Sorry, my brain's working a little bit weird today. I slept at 3. So, okay. So we have our B, we have our C. Okay, so now we plug it all in, right? I'll let you do that because we're getting short on time, right? But A is gonna equal to 1 over here.
B1.
This would be 1?
No, yeah.
-1.
It's -1.
-1. Gotcha, cool. Thank you for checking though. Okay, let's make sure that's right. A is -1. B is -1, A is -1, C is also -1. They're all -1. Okay, that's fine. Okay, so now we plug it all in, right? So our pi 2 is going to equal to basically your mu on the numerator and then dv rho. Any questions on pi 2? That looks good. Okay. So we're going a little bit out of order, or moving around the board here just to get room, but okay. Someone got the time again? Sorry, is that right? 9:50. 9:50? Okay. So step 7, you can check this yourself. I'll let you check it. If you take these pi terms and then you plug in from step 2 what you define them at the FLT system, they should be dimensionless. Okay, I will write it just really fast here. test rate. Okay, L cubed, L t squared, L squared, L to the fourth, ft fourth, ft L squared, 1 over L, t to L. Okay, and if we just look at this, I guess I'm kind of doing it for you already, right? L to the 5, L to the 5, FF. I'm missing a t squared somewhere. This is a 2, sorry. Okay, so that's dimensionless there. Pi 2, ft. We have L to the 4, L to the 4. We have t squared, then f. Okay, dimensionless. So basically, you're going to end up with 1 over 1, 1 over 1. And step 7 is important. This is a dead giveaway. I'm doing a quiz. I'm doing my final. It's not dimensionless. Something's wrong. And then it's your choice at that point in the exam. Should I spend time fixing this, or should I forget it, cut my losses, I'll keep moving forward? So, okay. Step 8. Oh. So you see, these fancy classrooms I've seen online, they will actually trace where you're going. This is what we got. Okay. So 8 and 9, there's in textbook you see 8 and 9, I just combine them. Step 8 is rearrange dimensionless variables, so that's your pi 1 or pi 2, if you want to express them in a certain way. And the reason for that, right, this is dimensionless, so if I take the reciprocal of this, it doesn't matter, it's still dimensionless. If I take this squared, still dimensionless. If I square root this, it's still dimensionless, it doesn't matter, right? So if for some reason you wanted to get it to a specific way, you can do that, right? And the reasoning why I'm pointing this out is because this pi term here, this is the reciprocal of Reynolds number, okay? So I'm just going to redefine pi 2 as dv rho over mu. Why? This is a Reynolds number. So they're the same. I shouldn't put equal sign, right? These should be defined. The dot means they're defined for their unit analysis, right? So I just took the reciprocal of that. Okay, and then after that, we're basically done, right? We go back to slides. Oh, see, this camera didn't see it. All right, camera. Pi squared, it took the reciprocal for Reynolds number, okay? Or pi to the 2, sorry. Reciprocal. Final step, we use this equation here, and that's your final answer, okay? So pi 1 as a function of the rest of your pi terms. This case, we only have pi 2. So pi 1 is equal to phi. Pi 2, okay, pi 1, that's going to be delta p. I have gotten lazy and stopped writing the L, but there should be an L there, subscript L. dv rho mu. dv rho mu. Okay. Let's just add it in there. Subscript L. Looks like an E. I don't like it. Okay, that's the 8 to 9 steps. I call it 8. I combine 8 and 9 together. Are there any questions on how this works? And if you see how I structure exams, it's like I had the concept questions, and then I have, it's not a freebie point, but it's kind of just a pretty straightforward problem where you should get the points. And the last exam, that was our manometry problem, right? So this looks pretty promising for final. Okay, no questions, we're good? Okay, let's see what time it is. 10:55. Okay, let's take a 5-minute question, yes, for a break.
For that final answer,
Yeah.
are you going to reciprocate pi 2 and not pi 1?
You could if you wanted to. In this case, I am not because that pi 1, I believe, is an actual equation that engineers use for pressure drop. So you could, it would still be correct if you took the reciprocal of pi 1 and did that way. But in this case, I just did pi 2 because I wanted Reynolds number, which we'll see. Okay, so 5-minute break and come back. We're gonna finish lecture and then start quiz. Like I said, I wouldn't stress out about the quiz too much. If you studied the homework, you should understand. Okay. Mm-hmm. Just so no one hears about your grades or anything.
This one, it's not related, but this is a separate problem series. It's basically the same thing you're doing on this. It's just a different formula. This is a condensed. It's and then this, I can show you the from the equation from the text, right? So it's the same answer you get.
Okay.
So use the same formula. 1,000, 9.1, 2 times.
And you had this already written down?
Yeah.
Okay.
It's just
Okay, if you send me an email about what you're showing me here,
yeah.
and then
I mean, this is just the solutions.
The second one
oh,
is
For midterm solutions. So
okay.
it's, yeah.
Okay, send me a picture of. I'll take a picture of this. Okay. Send me an email.
Okay.
Yeah.
So, that's part of the question. You have to like hold you the other side of the supposed to run to get opening. You mark me down because I didn't say that I used it doesn't ask for a mechanical system.
Right.
It's requirement.
So that is why I didn't explain it here. I added everyone when half percent. A lot of people have that wrong. Or not a lot of people, some people get it. So that's why it's not in your final grade here in the inside grade. In the final grade, it's plus 1.5. That's what it is. You only get a minus 1%.
Okay. And then because the force is directed in the negative direction, what would we need to add a negative?
So here, if you look at the solution, we equate the forces over pressure. So if you do it that way and move it over, that's how the negative will come out here.
Oh, the further to show that there's
I did it from the very beginning for the sum of forces.
and then you use U
So
and then.
this is
So-
F1,
I
assuming
actually
that it's
liked
going in this
it. I
direction.
kinda understood.
The one that I didn't understand.
So if you take this,
Overall but I only got
equal
through like
sum of
the
forces on the
first
right hand
problem
side,
and, like,
you'll
half
get
the second
FAX
problem. So
minus
I'm like,
F1,
okay, but-
and you move it
No,
over,
it
it's
wasn't.
going to be,
It was,
these sides are going to be flipped. So if you look at the equation,
It flips depending on how you set up the equation. I set up the equation based on the arrows that were already given.
right, so
I understand what you're saying. I'm telling you that is the answer because F1 is pointing in this direction. If you pointed the arrow that way, I would have put a negative.
right, but yours,
Because that would have been positive because it would have been set up. This is set up in variable form with F1 going in this direction.
right, so but this is solving for FAX. This isn't solving for
Still a
F1.
little rusty.
So yes, I agree with you.
I
This is fine.
accidentally
But this answer should be negative. All of these forces come this way. This was also negative.
Of course I know the derivative, but
So this is going this way, and this is going this way.
Correct. So if you have this, the somewhat forces FAX minus F1 on the right hand side. You solve that, you get the negative number for your final answer. And this is FAX. And this is FAX plus F1.
One more question. Most of the announcement about the project, you said you were basing grades based on effort. Does that mean the group meets all the requirements, but you assume that somebody else put in more effort because the metal requirements is going to lose points?
Right, so I guess I'm saying if one group does the continuity equation and the other one does like a complicated non-Stokes, I'm going to give the other group a little bit better grade.
Is that in the rubric for the project that you gave at the beginning of the quarter?
I could add it.
No, that's not how that works. You gave it, you assigned the project, you made our decision based on that.
Okay, I can I'll look at it. But I guess I'm just saying, right, I've seen the different group efforts here. One group really putting a lot of work doing CFD, things like that, and one's doing continuity equating, which is okay still. But I'm just saying, right, if there is...
But because the system that they picked requires a continuity equation instead of something more complex, you're going to doctor
Work ethics for this problem. So
Well, that shouldn't hold you back from putting more work into your project, right?
you don't know what defines it. It's not written up, it's not written anywhere.
Okay. I can try to update the rubric for that, but
Updating the rubric, so it can change.
okay, I will. I'm pretty sure I'm going to keep it the same. So I'm saying, right, sure, if you have a straightforward equation and you meet the requirements, I don't want to give you a definite answer now because I don't want to go back on it. So let me
You're already doing that. The rubric was your
okay, let me look at the rubric and I'll go back. Okay. Just because we have a foot and stuff. Oh, midterm, people over there. Sorry guys, we're going to have to wait till after class because we're running out of time.
Laura, quick, it's about the quiz real quick.
Yep.
I don't have my student ID.
That's fine. Just show me any driver's license ID.
I don't. I left all my walls.
Okay,
and
I
have
know
a
John.
picture.
That's fine. You're John, right?
Yes.
John. Okay, we're good. Okay, we're gonna get started really quick because we gotta get our quiz started, right? Okay, so example problem, we are done here. Reynolds number, I wanted to talk about it because Reynolds is down here, right? We solved for that for pi 2. That's kind of the derivation behind it. But this is probably one of the most famous or important fluid mechanics dimensionless parameter. Okay, so in short, this number distinguishes your laminar and your turbulent flow. So laminar, right, is smooth, parallel orderly flows. And right, turbulent is when your flow is kind of going crazy or chaotic. So an example of this, right, when I talked about Navier-Stokes and how there's that Millennium Prize for the $1 million, the equation doesn't work for non-smooth functions, right? If you're taking a derivative of that, I showed that in my lecture. That's a turbulent flow or chaotic. So the Reynolds number is just a ratio of the inertia forces divided by the viscosity forces of the element. And that's literally that ratio up there, right? So if you calculate this number, this is general terms, right? It could range from your scenario. So if you get from 2,000 to 2,300, that's generally laminar flow. If you get in between 2,300 to 4,000, we call that transitional flow, which is in between laminar and turbulent. And I think in your heat transfer or your heat transfer thermal class, they talk about transitional flow and temperature, right? And then Reynolds number, if it's greater than 4,000, it's turbulent flow. So here as well, if Reynolds number is really, really low, like less than 1, that just means the viscosity of the forces is just super dominant in your scenario, your problem you're looking at. So for example, if you have honey in your pipe instead of water, right, your numbers might not even be the same because the viscosity is so high in your problem. Okay? Very large Reynolds number. If you have something really big, I didn't want to put an exact value because this puts like 20,000 Reynolds number. And that just means your inertia forces are way stronger than your viscosity. So you almost have an inviscid flow, no viscosity. Okay, and this is just a figure of no separation, right? Reynolds number is 0.2, really high viscosity. And then this is an example of a boundary layer with a turbulent wake where your Reynolds number is really high, 20,000. So that just means this is almost like an inviscid flow, no shear stresses. Table 7.1 is basically a table of all of these dimensionless parameters, right? Reynolds numbers at the top. You can look into these and see what they're for, but this table is a summary of that. Models and similarity. Okay, so the reason why we kind of have these Buckingham pi theorem stuff, right, is it helps with experiments. So you can graph your pi 1 to pi 2, like I showed you, and have that smooth curve, and you can validate that with an experiment. So that relates to our next idea of models, right? So just looking at this picture, really simple. A model is usually a smaller scale of your actual prototype of what it's supposed to be, okay? And then you use these two to test something that you're interested in to actually get results. So like another thing I've learned at Boeing is that even though I'm a stress person, I learn a lot of mechanics of materials and use that every day. There are so many equations that we did not learn in school that I use because they have experimental testing and they develop their own equation. So it's not in your textbook and it's proprietary to them. So I guess if you ever go in the stress world like what I do, I guess just be ready to learn a whole new set of equations because, right, this stuff is a lot of assumptions of, right, non-viscous flow, ideal flow, things like that. So in the real world, they'll have experimental data, different equations. And this is just saying, right, we had this, I told you, your pi 1 term is equal to phi pi 2, 3, 4. So that is essentially putting your pi 1 is equal to your pi 2, 3, 4 terms, your other dimensionless variables. You can do the same for a model scaled down. And then you can apply that to your prototype. And that is all that is saying. Okay, announcements. While I pull something up, start getting ready for quiz, please. Clear your desk and put your equation sheets out. Okay, so midterm results, I try to have, this is just to help me guide me grade the exams, right? So I'm not going to post this, just so I made this so it's kind of fair for people. So these are kind of how the point deductions work. And I did, you start from full points, and depending on the reason, I had a minus 5%. And these subtractions are only if your solution's kind of in the realm of the problem answer, right? If it's totally not close, you're going to get much more than this 5%. And then I do a plus or minus 3 in increments of 1, right? So this could be a minus 8 to a minus 2%. You don't have to look into that, but that's just how I kind of grade them. Like here's another thing, right? If you have a wrong sign, you'll get a minus 2. You'll see everyone has got the same for that, like for the last problem. But a lot of people did get the answers right too. So here are our stats. So the mean was 82.4 after the curve. It's like a really small curve. Our technically before the curve, our mean was 81, which is pretty good because I think most of my classes, right, the average is around 75. So the curve from that 1.5, it's not written on your exam, the inside where I put the grade. That's due to that written problem that I had that was explain your answer. So in the actual exam, right, I said put a solution in. So, but you know, a lot of people did it and a lot of people didn't. So I just said, I'll give you the benefit of the doubt and I'll just add 1.5% for everybody. So that is why some people got more than 100 because they got the max and they got the extra 1.5. So I didn't want to dock people if they actually put it already, right? So yeah, this is a pretty good, looks like a normal distribution. Looks like class is doing okay. I guess just wanted to share that. Is there any questions on midterm grades? Okay. Okay, my to-do list, I need to grade your quiz 4 and your 5 I'm going to get back today. Project files, so they are due February 23rd. I think that's next week, right? So have those submitted to me by next week. So like I said in announcements, at minimum you need 1 equation from the textbook or in class. You could do your second one as well, but the second one you could come from a reliable source. I've kind of got some emails about maybe some group members not contributing properly. So like I said, if you let me know, I could put in deductions accordingly, right? And I put that before already when I showed the assignment. I said a minimum of 2 people, but if you like really show your work and you put your name, like I did this, and none of my group did anything, I can deduct points accordingly per member, right? Grades. Okay, so that third bullet point, right, because I'm open to things, right? I mentioned that grades will depend on effort. So I am gonna look into that and get back to you. And right, there's so many emails and stuff coming to me. So if you talk to me about something and I forget about it, just send me a note. I'm pretty good at replying to emails, right? I reply to people pretty quickly. So if you want me to look into something, let me know. So I'm gonna look into this bullet point right here to see, I'm gonna think about what I'm gonna do about that, okay? And then attendance, I am planning on taking attendance for the presentation dates that may affect your grade. It probably will. And the only reason for that is like, right, I don't really mind if you guys miss my lecture, but you know, this is for your peers. So, and I think it's only fair that if one person shows up to your presentation, you should show up to theirs. It's just kind of a honor system thing, right? So, right, I don't mind attendance for other things if you want to miss class. That's up to you to catch up, but these are for your own classmates. So please show up to these. Okay. There's perfect timing for quiz. Any questions about announcements before we start quiz? Okay. I will go around. Oops, let's do face down. Sorry. Take one, pass it down. Don't start yet, please. I'm going to look at equation sheets, right? Like I said, no written examples. If I see it, you cannot use it. Keep them face down. Okay. Do you guys mind just showing it to me really quick so we can get started here? I should have done this over a break, but hold on. Okay, we're ending recording.